The title for today's lecture is Differential Pulse Code Modulation, DPCM, and Delta Modulation, DM. So we are concentrating into two types of modulations, DPCM and DM. Look at the introduction. Then we have two main types, the DPCM, we look at its motivation, Predictive DPCM, how to predict, how to do the prediction, signal to noise ratio improvement, Adaptive DPCM. Then we'll move into delta modulation, also known as a variation. We have the adaptive delta modulation. So basically we have two types of modulations with some variations inside. Finally, we'll look at the bandwidth of the PCM. Alright, so when a signal is highly oversampled, which means we are sampling much above Nyquist rate, the signal will not change a lot from one sample to another. So basically, when a signal is oversampled, when we have high samples, many samples, we expect that the values to be very close to each other as we move from one sample to another. Now, we can use this fact and just look at the difference between every sample and the other. So to go from here to here, there is just plus 10, plus 9, plus 8. You can see that the absolute number was 2050. The next sample was 2060, but the difference between them is just 10. So if we concentrate on the difference, we have the differential quantization, which means I will just look at the difference. In differential quantization, we quantize the difference between consecutive samples instead of the original signals themselves, original values themselves. Why are we doing this? Remember that the error in the quantizer, delta nu over 2, is related to the values of the quantizer, the peak to peak, which is 2mp divided by L. So by looking at smaller values, a quantizer with the same number of bits but much smaller quantization intervals can be produced. Or alternatively, we can reduce the number of required bits. So basically two things happen. Either reduce the number of required bits per sample. The DPCM transmitter. Now that we talk about DPCM, let's see how do we build the transmitter and how do we build the receiver. We agreed that we're going to send the difference between the current sample and the previous sample. So we need a delay by one sample unit, delay of TS, where TS is the sampling interval. Now here we get the current sample minus the previous sample, and we get the difference at the output. So mathematically we can write dk as x of k minus x of k minus 1, the previous sample. Instead of taking the current sample directly to the quantizer, we can take the difference between the sample and the previous one, and now we quantize. We expect t to be much smaller than x, and now the output of the quantizer would be d sub q, the quantized difference. And this is simply the transmitter, DPCM transmitter. Now how do we build the receiver? Given dk, how it looks like this. The DPCM receiver, we will receive the difference, but the quantized difference. I need to add to it the previous estimate. So basically we have a loop again, we have a delay element. So I have an estimate of the previous value which will be added to the difference, and now we get an estimate of the current sample. Kind of the opposite or dual of what we did in the transmitter. So mathematically we can write the current estimate will be the previous estimate plus the difference. We add to it the difference. So what's the advantage again of doing DPCM? We recall this equation for the quantization error. The quantization power is related to the peak value, or delta nu, which is the step size, is related to the peak value. So by reducing MP, by reducing the peak value, we can reduce the quantization distortion. What's the cost added? There are two problems that might occur, which is first, error propagation, second, accumulation of quantization noise. We'll explain these two in the coming slides. But remember that using DPCM, which means relying on the difference, could result in error propagation and or accumulation of quantization noise. Let's look at an example. Okay, this quantization, the quantizer in this example used to quantize the difference. It has 8 levels quantizer, which means it's made of 3 bits. The way it works, it quantizes the values in the following range, okay, from -4 to +4, and the output quantization levels are the center values. So if it is in this range, it would be -3.5, and so on. Now in this example, I picked about 10 samples starting from -1. This is just an indicator. So 0, this is just an indicator, K counter. This is a sampled. This was chosen values given, provided from the signal, 0, 0.3, 1.5, and so on. Now what would be the previous value? It's just a delay, so we expect every element here to be moved to the next time interval. So of course here we don't know what was before, so we're just using 0. Now all samples are delayed by 1 unit. This is x of k, this is x of k minus 1. If you want to find the difference between two, we just subtract. So the subtraction result, according to this formula, would be just 0.3, 1.25, 0.7 minus 1.5 is minus 0.8, and so on. Alright, so now what is the quantization direction? What's the quantized values? Okay, basically, let's look at this first. The quantized value, you take the value in the center, so 0.3, the closest center level will be 0.5. This is 1, 1.2 would be approximated to 1.5, minus 0.8 would be minus 0.5. You notice that in all these samples, we are quantizing in an up direction, which means we approximate the approximate value will be more than the original unquantized value. So 0.3 became 1.5, 1.2, 1.5. Unfortunately for this example, it's all up until the sample where we sampled, we will quantize 0.7 to 0.5. In this example, we're going downward. Okay? Now we can see that if at the receiver side, what's going to happen? At the receiver side, we are going to use the following formula. Our estimate will be the quantized difference which would be received plus our previous estimate. Okay, so we'll start with initial estimate. Okay, what do? We add this to that, so you get 0.5. 0.5 plus 0.5 is 1. 1 plus 1.5 is 2.5. Again, 2.5 plus minus 0.5 is 2. You keep going, you keep applying the formula. Now, according to this formula, these are our previous estimates. According to our formula, we can just get this by adding the difference with the previous sample. So basically, we get our next values to be 0.5, 1, 2.5, 2, 2.5, and so on. This is our estimate at the receiver, and these are the true, correct, original values. So how do we quantify the error? The error will be our guess here at the receiver minus the original value. So 0.5 minus 0, 1 minus 0.3. You can see here that the error is increasing. Why? Because we have been approximating in the same direction. We have been increasing our approximation. So this is why, because we have up. This is an unexpected usually, but you can see that the error is accumulated. So 0.5, 0.7, the error is increasing until this stage where the quantization direction changed. Otherwise, error could accumulate, and we have large error here. Okay, so this is the example, and you can see here that the error direction was up, increasing until this stage, which was down direction. Okay, so that's the example to show the error accumulation. Of course, the error propagation will occur because once you have one, the next sample, the next value depends on the previous value. So making an error means the error will propagate, will move to the next, to the next, to the next. There is no correction mechanism. Okay, so now we have to find a solution. How do we improve our prediction? One way to do it is to use predictive DPCM. Now in predictive DPCM, we're going to guess the next value, and we are going to estimate and predict the kth value. We'll call it m hat k. What we transmit is the difference between our guess and the true value. So we guess at the transmitter side, and we also do the guess at the receiver side. So the difference now will not be mk minus 1. We're not subtracting from the previous value. We're trying to guess what the current value is. The better our guess is, the smaller the value of the difference, which means we have better quantization. Now at the receiver side, we first predict and then we find the difference. So we can call this a DPCM, or kind of, a predictive DPCM. We can think of DPCM as a special case of predictive DPCM, where our guess is the previous value. If you use m hat to be the previous value, it means that we are using DPCM. Let's look at this linear example. For example, a first order prediction would be to assume that your current value will be the previous value plus the difference. We assume that we have linear increase. Okay, so you estimate your current value by adding the increase to your current value. For example, this example will make it clear. For example, we have, this is again the sample value. This is the message itself, m. This is coming, this is provided to us. Now let's start guessing here. We cannot guess in the beginning, we need some history. So this goes from 0 to 0.3. Okay, I know that there is an increase of 0.3. What should be the next sample? I would guess it's 0.6. From here to here, I want to guess the next sample, but I know that the previous samples had moved from 0.3 to 1.5. There is a difference of 1.2. So I will add to my current value 1.2. So this would be 2.7. Again, I know that I am here, and the difference between the two values is 0.2. So I would add 0.2 the current to guess the next value, 1.2. This time my guess is perfect. Now, so for example here, let's pick one. If I am here and I want to guess the next value, 3.2, my previous value was 2.8, I would guess that there's a difference of 0.4, so 3.2 times plus 0.4 is 3.6, which is, this is my guess. The true value is 3.5. Now to find the difference between the current and the guessed value, or predicted value, you subtract, and we get even smaller amplitudes. Okay, you can see here that we have smaller amplitudes, which means we have less number of quantize. Now in general, how do we do the prediction? Okay, we can, according to Taylor series, if you want to know the future, you need to include more derivatives. You need to talk more about the past. So knowledge of the prediction depends on how much values are used from the history. For example, the simplest prediction will be just to take the first part of the derivative, the first derivative, and we can approximate the derivative by the difference between the value and the previous value. Okay, divide by the time. The time will cancel in, and we get the first order prediction, which I shared with you in the previous example. All right. So this was the previous example. Now, of course, if you want to make things more complicated, you can guess based on not just the previous sample, but the sample before and before. Depending on how many samples you take, this is called nth order. It's called nth order prediction. Okay, so nth order predictor will be of this sort. The larger the value of n, of course, the better the prediction, but of course you need a delay and buffer. Okay, for the prediction, this is again the equation, the nth order prediction, and here is how the circuit look like. Take the current sample, and we need a buffer delay to store the previous values, weight them, add them up together to make up your guess. So basically use history to come up with the current or the future value. Of course, the bigger your history that you consider, the better your guess of the future. This is kind of using experience. Now we can analyze the differential DPCM in the same way. And this is, we're using color code just to allow you to map. Okay, so basically this is how we do the guessing at the transmitter, the DPCM. I will have my input signal. I will generate my local prediction, which we call m hat q. It's hat because it's prediction. Subtract from the current sample at the receiver. This is the receiver side. So basically I'll have my local prediction, add to the difference to come up with the quantized value. At the transmitter side, what I do, I have kind of full receiver. The same receiver here is kind of flipped here, because at the transmitter also we need to make a guess. So we have the input signal, we do the job of the receiver to guess the current sample, and then we get the difference, quantize the difference, and we get DQ. If you want to follow the math with the color code here, you can see that the kind of purple color here, DK the difference equal to m minus the prediction. The quantization now would be the difference signal with Q, which is nothing but the quantization error. At the receiver side, you can say that the final guessed output is made of MQ, which is the case quantized, plus the quantized difference. This plus that give you the output signal. Now I'll use the previous equation. Okay, remove this red signal is now equal to D minus MK, or MK minus D. So this is now produced from the first equation. This is nothing but the quantization error. So for basically that the received signal quantized will equal to the transmitted plus quantization error. Okay. Now you can see here that at the transmitter side, okay, what happened if somebody decided not to include the quantization? So he's doing the prediction. Can you see this dotted line? Okay, if you have this short line, the analysis will be different and the error will be more. So we need to include the quantizer in the loop of the transmitter to be similar to the receiver. For the signal to noise ratio improvement, we're going to have improvement for the signal to noise ratio, and this signal to noise ratio improvement can be referred to as GB, the processing gain. The gain, it's the processing gain, it's the gain that we get by thinking. It's the power of the original message divided by the power of the difference. Okay, how much gain we have, we can compare the power here, how much improvement. So this is the power of the message and the power of the difference signal. In practice, the values that we expect usually is about 25 dB for voice and low activity images, and that's of course a very good amount of gain, huge gain just by thinking. Alternatively, for the same signal to noise ratio, if we don't want to get the gain in terms of signal to noise ratio, the bit rate can be reduced by 3 to 4 bits per sample, huge amount of reduction. So telephone systems, for example, use DPCM, and they can often operate at 32 or even 24 kilobits per second instead of 64 kilobits per second. By looking at the difference, we reduce the requirement from 64 kilobits per second to only 32 or even 24 kilobits per second, because samples are correlated. Okay, so for adaptive differential DPCM, we can control the adaptation. We can make the delta V adaptive, which means it changes with time. So I can compare it with 0 and delta V. And if you find it very close to delta V, we can increase it. If it's very close to 0, we can make delta V smaller. So an 8-bit BCM using adaptive DPCM can be reduced even to 4-bit ADBCM at the same sampling rate. Almost we get half the number of bits, or a factor of 1/2. The ITU, the International Telecommunication Union standard, one of the standard is using this technology, adaptive DPCM, for Microsoft Wave. Remember, if you have sound wave in Microsoft Windows, you can store it as a file.wav. It uses the same adaptive DPCM technology. Okay, in delta modulation, we have one example of DPCM. The special thing in delta modulation is that we have a 1-bit quantizer. This quantizer produces 1 bit. It's 2-level quantizer. It's a comparator. It compares the incoming signal with 0. Is it positive or negative? So our quantizer reduces 1 bit at a time. Otherwise, we have the same loop as a DPCM. Our prediction here, our guess, is just an accumulation of the previous bits. This is an integrator or accumulator. It counts, it adds all the previous data. So then we subtract the incoming signal from the guess to get the difference, and then quantize that. At the receiver side, the outcome will be just an accumulator followed by a low pass filter. Now, what is the motive to think about delta modulation? Why not just continue with PCM? There are problems with PCM. For example, a loss of frame synchronization would destroy everything, because we have groups of bits to represent every pulse. Once we lose the synchronization, everything will be lost. And delta modulation is a special case. Delta modulation is a special case of DPCM, which is only 2-level quantizer. The difference now which used to be the message minus the previous message, is quantized only using 1 bit. At the receiver side, we have a low pass after the accumulator, which will smooth out the output, because the output will look like staircase, and then once we use a low pass filter, it will be smoothed out. To use is it possible to use 1 bit quantizer? What makes this possible is that we are sampling at much higher than Nyquist rate. So in delta modulation, we're sampling at 30 to 40 times above Nyquist rate, much more than that. Now, this is possible because we are only producing 1 bit per sample. Why are we sampling at high look like in signals? So basically, this is the start signal, and this is the quantized signal using delta modulation. We assume we'll start from initial value, so at startup there is some error, of course, where we start to follow up with the signal. So it says go up, we have 1 bit up, 1 bit up, 1 bit up, and then we have to go up, down to trace the signal. So only one thing to be done at a time, either up or down, either up or down. Okay, what you see here is a quantized difference, which means positive means up, 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 down, up, up. So this curve is a translation of the difference between the true signal and the quantized signal. So basically we can say that the quantized message is a staircase approximation of M of t. We can of course use a low pass filter to smooth it out. So we send positive DQ when the message is more than our guess. Okay. Otherwise we'll be sending a negative, which means go down. Now there is a few things to note here. How much is the step size? And should it be large or small? Now we have problems here. Now if your message is constant, then you get a kind of error that's called granular error, because you have to go up and down, up, down. You fluctuate between positive and negative. It's small error, it's granular error. There's another type of problem which is very serious. That's if the slope is high, if the derivative is high, if your message changes dramatically, then the sampled signal or the quantized signal will not follow your signal. This is called slope overload. That's the slope is too high to be followed. Slope overload. So to sum up, there is a problem in the startup. There is a granular error. This occurs when we have constant signal, almost constant signal, or small variation, and the slope overload occurs when we have fast change. One solution to this problem, we can use adaptive step size, adaptive delta modulation, which means if I notice that I have a long sequence of positive or negative, it means I am going in one direction, either up or down. So why don't we increase the step size? And if I notice that I have oscillation positive, negative, it means the signal is almost constant. So why don't we decrease the step size? So we can make an agreement, for example, if we have 5 or 4 ones or positives or 4 negatives, we can increase the step size, and if it oscillates, we should decrease the step size. Of course, an agreement, clear agreement between the transmitter and receiver should be established. Okay, quick comparison between differential DM and PCM. In DM, each digit has equal importance because each digit says up or down. In DM multiplexing, each channel requires its own decoder because we are accumulating, we are depending on the previous values. However, in PCM, one decoder can work for all. Okay, that's in terms of hardware account, PCM is better. Okay, but in terms of possible crosstalk, DM is better because DM has separate decoders and they will not interfere with each other. Delta modulation outperforms at low signal to noise ratio. This is a piece of information because we're not doing the analysis. Here we are told that DM outperforms PCM at low signal to noise ratio, while PCM is better at high signal to noise ratio. Delta modulation is very simple, inexpensive, and no need for framing bits, which means we have less overhead. Delta modulation is suitable for voice and TV signals. Now the last slide, which is very important, the bandwidth requirement for digital. We have talked about the bandwidth requirement for analog. For example, if you use a double sideband AM, starting with the bandwidth B, you need a bandwidth of 2B because of double sideband. For single sideband, starting with bandwidth B, you need B. Now, how about digital signals? The bandwidth required for binary baseband, if your signal is not modulated, if it's in baseband, it's half of the rate. So if you have 10 megabits per second, you need 5 megahertz. If you have 20 megabits per second, you need 10 megahertz. However, if your signal is passband, it's modulated, it's shifted to higher frequency, then the bandwidth will be doubled, which means the bandwidth requirement now will equal to R. For 10 megabits per second, you need 10 megahertz of bandwidth. For 100 megabits per second, we need 100 megahertz of bandwidth. That's for binary baseband, it's R over 2, and for binary passband, it's R. Thank you.